In this module, we will define the term probability and learn the 3 probability axioms. Now, as far as the definition of probability is concerned, there is no one or single definition of probability. There are many. Indeed, we will look at 3 different definitions of probability in this module, which are all useful in one way or the other depending on the situation. The first definition of probability is as the ratio of number of favorable outcomes to the number of total outcomes. For example, if we consider the tossing of a coin, and if I ask you what is the probability of getting heads, then you will say that the probability is half without actually performing the experiment, because there are 2 possible outcomes, heads and tails, and the event of our interest is heads. So, the probability of the event of our interest is simply the number of elements in A upon number of elements in the sample space, which is half. It is a useful definition, but it has 2 limitations. Number 1, the outcomes are assumed to be equally likely. For instance, in this example, without having said that the coin is fair or unbiased, we actually assume that the coin is fair, and therefore both the outcomes heads and tails we assume to be equally likely or equiprobable, and therefore computed the probability to be half. But this may not always be the case. Another limitation of this definition is that it assumes a finite number of outcomes, which may not always be the case. So, there are 2 limitations. It assumes outcomes to be equally likely, and it assumes finite number of outcomes. So, when this is not the case, we need to resort to the second definition. But before we go for the second definition, one point worth noting about this definition is that here we compute the probability without actually performing the experiment. We did not actually toss the coin to tell the probability of getting heads is half. So, this probability measure is given without performing the experiment, before performing the experiment, and therefore also termed sometimes as a priori, before the experiment probability. And when this does not work, we resort to the second definition, which is what we call the relative frequency definition of probability. And here we actually perform the experiment a large number of times, actually count the number of favorable outcomes and divide that by the total number of experiments performed, and then compute the probability. Because it is computed after the experiment, it is also called a posteriori probability. Posteriori means after the experiment. Mathematically, if you consider an event A, the probability of the occurrence of event A is the number of times A occurs upon the total number of times the experiment is performed in the limits as n tends to infinity. Well, it is not in the mathematical sense n tends to infinity, but that simply implies that the experiment is repeated quite a large number of times. It is a very useful definition, but one limitation with this definition is that it may not be practicable to repeat the experiment a large number of times, and therefore we need to resort to the third and the most useful definition, the axiomatic definition of probability. In a sense, the axiomatic definition is a canonical definition or universally adopted definition because it fits all situations. consider a sample space, a probability space omega f p over or for a random experiment H also consider two events A and B in F, then the probability axioms say that number 1, axiom 1, probability of A is always greater than or equal to 0. This is called the non-negativity axiom of probability measure. The second axiom says that probability of the certain event omega is 1. It's the normalization axiom, or this axiom provides a normalization to the probability measure and therefore restricts the probability assignment in the range 0 to 1. And the third axiom says that the probability of union of A and B is equal to probability of A plus probability of B, provided that A and B are mutually exclusive. This is known as the additivity axiom of probability measure. This axiom can be generalized to n events. So, in general, if there are n events a1, a2 up to an, which are all mutually exclusive, then the union of ai's, I from 1 to n, probability of them is the sum of the probabilities ai, I from 1 to n, and it can be proved easily through mathematical induction. So, in this module we looked at the three definitions of probability. One as a ratio of number of favorable to number of total outcomes, which is a priori definition of probability. It has two limitations, that it assumes the outcomes to be equally likely and it assumes that the number of outcomes are finite. The second definition, which is the relative frequency definition of probability, is a useful definition, but it may not be practicable to repeat the experiment a large number of times, which is the requirement for this definition. So, finally, we need to resort to the third, the canonical definition, the axiomatic definition, which is based on three probability axioms, namely the non-negativity, the normalization and the additivity of probability measure. So, that is all for this module. Thank you.